Welcome to the webinar. My name is Denis Vrdoljak. I am your presenter today. We are in a Web Age Solutions webinar. We did an Accelerate. The two companies have merged under the Web Age brand. We did an Accelerate webinar a week ago on ChatGPT, and this week with the Web Age webinar, we are going to be talking about generative AI and also showing how to build a custom model that can then be incorporated into an application. So first, a word about Web Age Solutions. Web Age is a IT training company, and at Web Age we offer training both in person and virtual on everything from Microsoft and data privacy, Java, C++, JavaScript, web apps, all the way to data science, data engineering, machine learning, DevOps, and everything in between. So if you have any training needs, that's on the next slide. If you have any training needs, don't hesitate to contact us. And this is a 1-hour webinar on generative AI that's also a bit of a teaser to our 3 or 5 day training program that goes into a lot more detail than what we'll cover in this webinar. So if you are interested in learning more, don't hesitate to reach out. I'll have the emails and links here in the next slide, one after this one. Upcoming webinars are listed at webagesolutions.com/webinars, and there's also webinar recordings. So this recording will be shared with everybody that's in the audience, as well as being posted with the other recordings on the YouTube page. And this webinar showcases some of the offerings that we have in machine learning. And here we are just kind of highlighting a couple of the offerings, generative AI engineering being a full-blown course, more than just a webinar, as well as fundamentals of deep learning, Python, data science, data engineering. We actually just revamped the data science bootcamp and also have a machine learning bootcamp. So if you are interested in those programs for your team, reach out at these phone numbers and emails. I'll leave those up for a second for the recording, or if anybody wants to jot them down. I'll show the slide at the end again, so if you don't get it all, it is actually, you can just go to webagesolutions.com and go to the contact us page. All right, let's get into the webinar. My name is Denis Vrdoljak. I have been doing data science for a while, more than a decade, and doing machine learning work for a full decade now. And specifically with generative models before LLMs and ChatGPT and all of those other tools that have really made the news and headlines in the last couple of quarters. We were building generative models, just generative machine learning models. And we'll talk a little bit about what those generative machine learning models are and how that's evolved into generative AI. In this webinar, we're going to cover an overview of generative AI. We're going to talk about language models and large language models, and specifically generative large language models. We'll talk about what are the components of these LLMs, as well as go through a step-by-step build of a custom LLM, or an LLM specifically that will be based on the GPT-3 DaVinci 2 model, and we'll show how to customize it to some data that the model has not seen before, and how that can be used to build a custom application with the DaVinci model. And then finally, we'll compare the results between our new model and the original GPT model and see some of the differences in what it can answer and what it knows in its knowledge base, as opposed to what the base model does or does not have. So first, the obvious question, what is generative AI? We'll define it properly here in a little bit, but let me first define it with some examples. ChatGPT, which uses GPT-3 and GPT-4 models under the hood, is a chatbot style interface where you can ask the model different generative questions, different free text questions, and it'll give you a text response. Another implementation of this is Jasper, which is a very similar interface, also based on ChatGPT, where you can, as opposed to just giving it free text, you can give it prompts like the description, keywords to include. You can give the tone of voice request in ChatGPT as well, but here it separates it out, as well as giving us some more control over it. Just a different implementation of a generative AI application built on top of a generative LLM. There is the underlying model itself. Let me find my mouse pointer here. There is also the models themselves. If we take the DaVinci 3 model, 003, that we'll be using later, we can ask it what is generative AI and see what kind of response it can give us. And then, of course, we can query these models by hitting a API endpoint and capturing the text response or the GET request response programmatically, and then parsing it and building it into an application. And we'll come back to this notebook with some examples in a little bit. So some of the other questions we'll discuss is how are generative models built? How do we customize them? And in this presentation, we're going to focus on language models. In all of the modern cases, they will be large language models. We will not be covering much on image generation or video generation or other types of audio generation, music, other types of generative AI. We'll mention it when we get to a couple of the topics based on how we build generative AI, but we'll mainly be focusing on the language models. So for our overview, I guess I got a little ahead of myself with the example. What is generative AI? We can demonstrate that by showing how ChatGPT reaches into the GPT underlying generative AI model, similar to how Jasper does it, or the direct API call that I showed you guys. And it essentially generates some new content. That's more or less the gist of what is generative AI, that instead of classifying the content, like this prompt that I gave it, what is generative AI, it's not trying to classify that into some category or predict some score for it. It's generating new content in response instead. Now, to use it in applications, we'll want to be able to, well, first customize it. Otherwise, we're just stuck with out of the box with whatever the creator of that LLM has thought to bake into it. If we want to customize it or update the knowledge, we'll want to be able to fine tune it, and then also build a API endpoint so our application can interact with it. So first, we'll talk a little bit about machine learning basics and generative models to set the stage of what we're talking about. Those of you that are already data scientists or machine learning engineers, that first section will touch on a couple of interesting points. So it'll be a little bit of a review for you guys, but get everybody else up to speed. And the next section, we'll talk about the building blocks that are used to build LLMs. We'll talk about how they're actually built and created and scored. And then we'll go to fine-tuning our own LLM and creating an API endpoint that we can then use for our applications. And we'll wrap up with some final thoughts and conclusions to bring everything together. So first, we start our journey in the 1950s, in 1958 and 1959. The perceptron was created at the end of the 1950s, which is the basic building block of our neural networks today. The term machine learning comes from the late 1950s as well, from a self-learning checkers program. In the 70s and 80s, there was one of the AI winters, as they call it, and there was a lot of focus on rule-based systems. Machine learning systems are statistical systems. Rule-based systems follow a fixed set of logic and rules, as opposed to having statistical results. The 90s saw a revival of machine learning algorithms, especially with developments and libraries coming out with decision trees, k-nearest neighbors, SVMs, which led to more interest and also more funding into machine learning. We also got some of our ensemble methods like random forest and boosting, and XGBoost came out a little bit later, but some of the tools that let us leverage multiple models and build something even bigger. And with that, the models got bigger slowly. And then in the 2000s, big data, the internet really, and all the data that was being collected led to the need for some type of non-human machine process to analyze all of that. And at the same time, deep learning came to the forefront to help make sense of it all. This was made possible by some of the developments in neural networks, like the convolutional and recurrent neural network topologies. And then in the 2010s and early 2020s, we see advances in computational power. These really led to the breakthroughs in machine learning. Prior to this, the bottleneck wasn't memory. There's plenty of memory and RAM and flash drives to hold all that data, and we had Hadoop and Hive to store the data, but trying to process it was the bottleneck there. And so the advances in computational power and advances in GPUs really drove the advances in machine learning. And we have our friends in the gaming industry to thank for some of those breakthroughs. Also in the 2010s, models like BERT and ELMO revolutionized natural language processing, or NLP. And then in the late 2010s and going into the 2020s, we started to see GPT-1, 2, 3, 3.5, now 4, along with all of the other transformer-based models. This all got kicked off in about 2017, 2018. At the same time, adversarial networks pushed the boundaries of what's possible. They were used originally a lot in image generation, another form of generative AI. And then finally in 2017, and after that, the transformer and attention-based models led to today's large language models. So when we say generative model, this is a subclass of a machine learning model. Essentially, it learns the distribution of the data that it's trained on, and then it's run in a way where it generates new outputs with some variation, because you probably don't want the same output every time. But it creates new data points as opposed to classifying or regressing on the existing data like a lot of other machine learning models do. Just a couple of the more common types of generative models that are underlying topology. Transformer models led to the current GPT families, plural, GPT-1 through 4 families of models. GANs also led to a lot of advances originally in generative image generation, as well as in other things like cybersecurity. The Google Alpha system that beat the world champions in Go was a GAN, a generative adversarial network, where two AIs played Go against each other to learn how to play it better, and then they went and played against humans and beat everybody in the second and third iteration. There are autoregressive models, which, to overgeneralize them, they are used in LLMs like transformer models, but they focus on a probabilistic modeling of what the sequence being a sequence of words, for example, for LLMs, what that would look like to be able to predict the next term. There's also variational autoencoders, normalizing flow models, energy-based models, and a few other ones. But the ones that we'll see in LLMs will be transformers, and in the later GPT families, also autoregressors. But that's getting ahead of ourselves. A generative model is just a model that generates some new output. So we're going to run through an example where we created a simple naive Bayes classification model. It's trained on the MNIST dataset. The MNIST dataset is a dataset of digitized handwritten digits. It's the type of data that the post office's scanners that automatically direct mail based on the handwritten address might use. I don't think that those scanners are trained on the MNIST dataset, at least not today's versions, but it's that type of data set. We'll have some examples of what it looks like. And so in this example, we'll basically build a naive Bayes model as a classification model and then run it in reverse to generate new handwritten digits. So our training data looks like this. It's the numbers 0 through 9, centered. The tick marks on the X and the Y axis are just there for reference. The image itself is just the number handwritten with all the different variations of how people write those numbers. And you might see that there are some problematic ones, like some of those 9s look like 4s and vice versa, especially that 4 at the bottom. Specifically, a couple of examples that were problematic in the data set are these 4s, I believe. And you also have to keep in mind that when you go to the original data, some of those might even be mislabeled. So there is noise to the data. It is an imperfect system, and the machine learning model will be imperfect. Now, if we wanted something that perfectly classifies the number every single time, we would prefer perfection. But if we're building a or going to use it as a generative model, well, then that noise is actually beneficial to us because we have the variety of the different ways of representing these numbers in handwriting in the population. So to build this, we'll pre-process the images into a numerical data set. It's a 28 by 28 grayscale bitmap. So we'll basically turn it into a matrix of 28 times 28 bits. or values, not bits. We'll train a naive Bayes classification model to the digits using 0 through 9 as our 10 classes. And then we'll run the model in reverse and add some random variation to be able to run it as a generative model. And if we run it as a generative model, we get something like this. Every single one of these numbers is generated by the machine learning algorithm. These are not handwritten. You can tell because they kind of seem a little bit pixelated. In this very simple example, the results aren't smooth. It's just the very basic generative machine learning by running a naive Bayes in reverse. With the random noise, you can see that there's some differences in how some of these are written. If we did this with the random variation, we have a very basic example of a generative model. But the same approach is also used to analyze what part of the image is actually used by the machine learning algorithm to identify different patterns. This is still used today to analyze, to kind of get a glimpse into how the machine actually sees and what it's looking for optimization. But with the variation, we get a generative AI. I say that hesitantly because it's a very basic one, but we get our first generative AI there. Great, so we can create our own handwritten numbers and letters. That's nice, but we can't really talk to this machine learning model. So let's start looking at some of the building blocks that we'll need to be able to have large language models. So not long after machine learning, what led to what is today called NLP, or natural language processing, started in the 50s and 60s as well. Back then, it started with rule-based algorithms translating Russian sentences to English sentences. There were some speech recognition experiments in the 70s and 80s. And in the 90s and 2000s, machine learning enabled NLP to really take off. Originally, it was just things like random Markov models, Markov chain models, naive Bayes state vector machines used for text classification or sentiment analysis, which was extremely useful, especially when you think about all of that web data and not having humans that can classify that much data. So this led to some advances there. And then with advances in neural networks in the 2010s, this is where we got our CNNs and RNNs, which we'll talk about as an important building block for our large language models. LSTMs are another important building blocks. We got some models like the Word-to-Vec and GLOVE model. And then later we got transformer models and neural network architectures that have attention, starting with Elmo and BERT and leading up to GPT-1 and then 2, 3, and 4. And this kind of culminates or hits a landmark in March of 2022, where GPT-3 was released along with its codex, which was able to understand not just English, but also programming languages. And so you could tell it, give me this thing I'm describing in English, but give me the result in Python or JavaScript. The early results on that were not great, but the current results are actually much better than back in 2022. So the first thing is that really led to the breakthroughs in modern LLMs is attention. So our original neural network topologies like CNNs and RNNs had limitations. They are still used along with LSTMs as a building block to create our attention mechanisms. But those early models were things like Word-to-Vec and GLOVE, where it represented a sentence as just the collection of the words. Without having any context of which words come first or second, you could code that into the model as additional features, but in its basic implementation just takes what's called the bag of words approach, where it just treats all of the words in the sentence as a bag of words with no attention to its context, pun intended there. Next, we got attention mechanisms like Elmo and BERT, and then transformers. Elmo had unidirectional attention, BERT had bidirectional attention, and then transformers were built on a Google research project and research paper that came out in 2017. It was called Attention is All You Need. And the topology there led to the huge advances in NLP that started in 2018 and going forward. GPT-1 came out in 2018 based on that architecture. That image on the right is the topology of GPT-1, a bit abstracted away, not giving you the individual neurons and their connections, but that is actually GPT-1. And then GPT-2 had big advances in sometimes this has been called on the marketing side as natural language understanding, NLU, where it's the ability to understand what it is processing or what it is vectorizing, working with, as opposed to natural language generation or NLG, which GPT-3 advanced, where it did a really good job generating human-like speech. The emphasis on human-like, because any model, including Google search autocomplete, will generate text for you, but it might not be very human-like. It might not be very conversational or useful. So those advances came out in GPT-3. Attention was originally introduced in machine translation, and it allows the model to focus on different parts of the input when producing the output. So basically gives it attention to the context, the words around the word that it's looking at, if it's looking at single words or n-grams or other tokens at a time. And that gives it the context of what it's working with. At the micro level, if you think of the word in a word in any sentence, like attention in this last sentence, the word attention means something different when we're talking about machine learning than when we're talking about paying attention during a webinar or in class or during a meeting. And so the surrounding words give it that context, which changes the meaning of that word and the whole sentence. When you think in terms of more of a macro level, like when you're working with sentences and paragraphs, being able to have a larger attention window gives you the ability to understand an even bigger context of what you're talking about. Elmo wasn't the first model that had really any useful attention, but first one that was popularized. And it represented words as vectors and used bidirectional LSTMs. LSTMs are long short-term memory. They're a neural network architecture. So use bidirectional LSTMs to be able to capture the pre or post text as context. BERT advanced this and enabled bidirectional context so that it could take into account the context both before and after. And if we take a look at this, we can see that the LSTMs are the building blocks of Elmo. I'm not sure if you guys can see my mouse circling over that, but in BERT here on the far left, it's actually using transformers instead of LSTMs. And if we take a look a little bit into the future of where we are in our history here. GPT at a high level abstracted kind of 10,000-foot view has a similar architecture to BERT, or some architecture that you might think is inspired by it. There are differences, especially on the decoder part. It's kind of hard to notice, but even on this diagram, the connections at the bottom are different between BERT and GPT. This will be GPT-1. That's one of the big differences, that GPT had a better decoder structure that could do natural language generation. So I've said encoder and decoder a few times. That's another building block. Essentially, if we take our input data on the left in the blue, and we take our expected data, we expect to be able to reconstruct it, and we basically compress it to a smaller number of neurons. This is called these middle layers are called our latent space. That first half of the network is an encoder. This will be an autoencoder if you were running a neural network that looked like this, where it squeezed the middle and then tried to reconstruct the data on the outside. This lets you take the hundreds of thousands, millions of words, phrases, tokens in a language and compress them down to a feature vector where you can then work with it in the neural network without having to have a 1 million by 1 million size neural network. Autoencoders will typically just take the encoder and then turn text into vectors. And this is part of what's used in BERT. And the decoder part of it is for a lot of NLP tasks like sentiment analysis and text generation thrown away. But it is important for being able to reconstruct the data because this is the part that brings it back to its original form or as close as we can get to it. Now, when we're talking about large language models, some of the units that we use are recurrent neural networks. And the big benefit of RNNs is that it has a feedback loop which enables attention from the previous point in the network. The downside of that is that that has a vanishing gradient problem, which LSTMs address. Address this problem, which essentially would normally cause the model to forget what it had learned in the previous training iterations, passes through the data epochs. LSTMs address that problem, but at the expense of learning rate, usually. Transformers are a more recent architecture where they have an improved attention mechanism, and it is the topology that's used in GPT-1, also used in BERT, and is going to be important. We'll actually see topologies where it's a mix of transformers and LSTMs in later families of large language models. Some of the features of a transformer are that it has a self-attention mechanism where it's able to consider the context of the tokens that came before and after the one that it's currently looking at. And so with this, it's able to better understand sequences, like natural language being sequences of words. It has positional encoding, which means that it can capture the position of a token, or in a language model, of a word or phrase in a sentence. And then it also has layer stacking and an encoder-decoder structure. And then another important thing to mention is fine tuning. So typically we don't want to build a brand new model for every single task. And so it's important to have an architecture where we can fine tune a base model to customize it for specific tasks. For example, think of uh, everybody that goes through school learns the English language, and then some people go to uh, become data scientists or data engineers, other people become lawyers, other people become welders and mechanics, and all of those specialties, all those job skills kind of require that base knowledge of the English language that everybody starts with. It's very much the same way where you start with the base model that has a certain base knowledge. Often it's the understanding of the language that's the base model. So just a generic large language model. And then from that, you can fine tune it to specific tasks or teach it new relationships, new concepts that are not part of the base language. When we're working with training data, this is kind of specific to the architecture that you're using, but some of the uh, data formats are masked data. BERT and GPT-1 use this where the a sequence of data, for example, in BERT, if you're working with sentences, the sentence of data, you mask a single word or multiple words, and then train the model to predict that word based on the surrounding words and the position in the sentence. Question and answer data, kind of like the prompts and responses that we looked at as our examples right at the beginning. Summarized data versus the full data, kind of think of that as another version of the question and answer. And then for translating languages, having the same text in multiple languages. So English and French to train a model to translate from English to French and vice versa, or a description of the program and the code for the program in Python to train the model to essentially generate code. And generating code is conceptually not that much different than translating to a different language, because the programming languages follow a strict set of rules which a large language model can learn, and that gives us the ability to translate from one language, English, to another, Python, just like if it were French. But when we're working with this data, we can't use our standard cost functions for scoring the model, and typically we want to minimize the cost function. Some of the cost functions that come up with large language models are perplexity, which measures the surprise of the response. And a lower score is better because if you're testing your model with either a question answer or prompt response, you don't want to be surprised by the response. You want to get the expected answer. So cross entropy loss is basically a measure of information loss, entropy being the inverse of information gain in information theory. It's a measure of the information loss between the generated text and the true text or the correct text. The blue score is used for models that are used for translation between languages. And so this one measures the accuracy of tokens like n-grams. Actually, the blue score looks specifically at n-grams. I'm sure it can be adapted to also look at skip grams and things like that, but that's the blue score. The rogue score is used to test for text summarization. And then the squad score is used to measure the ability to do question and answer, where it basically measures the similarity between the given response and the expected response by looking at number of exact matches and overlapping words and phrases. When we're looking at some models that are not language models, we have a couple of scores like the inception score and the Fretch inception distance score, which are used to score how well images are generated. First one looking at the diversity of what's generated compared to the diversity of the original real world image data set. The second one looking at the distribution of features in the generated versus real world data. We have a precision PRD score, a precision recall and recall for distribution score, which is also for images. We have a maximum mean discrepancy and a bunch of others for different types of generative AI models. But the takeaway here is, if you see some of these ones on the previous slide, these are used for language models for different applications, as opposed to just having a correct answer like you might expect in a classification or a regression problem. Okay, so let's take a look at building an LLM and taking a base LLM, fine-tuning it, and then setting it up for an application. So fine-tuning is a type of transfer learning. Essentially, abstractly, the knowledge is transferred to the new model or carried over to the new model, and new knowledge is added to the fine-tuned model. The way this is done is by adding layers to the neural network and then freezing ones in place to preserve a certain amount of knowledge, but learn new knowledge. And this lets us leverage existing models instead of having to train from scratch. What this conceptually would be is that you would take a pre-trained model, turn it into your base model, you'd freeze certain layers so that they can't be changed in the learning process, add some fine-tuning layers, and then find the right learning gradient and train the fine-tuned model. To choose a model for computer vision, there's a bunch of good base models. For NLP tasks, there's of course the GPT families of models, Word2Vec, BERT being common ones for classification and sentiment analysis types of NLP tasks. And then of course the GPT family of models. Models are getting pretty big, especially GPT-3 and 3.5 is a little smaller, but GPT-4. So with these ones, we will get a API interface to do the fine tuning for us. And that's really nice because without the API, we would have to take our base model here on the image on the left, remove the classifier, add some fine tuning layers. We then have to figure out which layers to freeze in the model, and then set it up so that we freeze those layers and apply the fine-tuning to just the fine-tuning layers, because we don't want to wipe out the existing knowledge. We want to preserve that. We just want to adapt it to new knowledge. And then you have to add your trainable layers and then fine-tune the model. But when you get to LLMs, it's not that easy because the different stages of an LLM act like as part of it. The layers in the beginning will tend to cover the NLU types of transformations for the overall system. The later layers will have the NLG layers, which will bring the response back out of the vector space and back into plain text. So knowing which layers to freeze in an LLM is very much non-trivial. Knowing which layers to freeze in a BERT model is something that the model was designed, and the paper on the BERT model included an explanation of how to do that. So that's a little different than taking something like a GPT model and trying to work with that. So fortunately, there is an API where all of that is done for us. And what we're going to do is take a Da Vinci model, Da Vinci 003 model specifically. This is a GPT-3 family of models. GPT differentiates itself over some of the other language models by having a autoregressor in addition to a transformer topology, and having differentiates itself from BERT with the decoder stage being very different than how the BERT model is built. And so in our case, we're going to take a cloud-based API that OpenAI will give us and fine-tune it. So some things that we're going to add is information about the company BDSG. The Da Vinci model has never heard of BDS. Well, it's heard of BDSG, but it's never heard of Berkeley Data Science Group. It's heard of other companies called BDSG, but not the data science company called BDSG. So it has no idea that exists. It also knows the years that President Abraham Lincoln went to school, but it doesn't have a concept of the length of time that that would be. And so first we're going to take a look at the data that we're going to use. So for fine-tuning a model, we will essentially have question and answer style data, essentially prompt response. So if we take a look at the data here, hopefully that's not too small, but we have the prompt and the responses essentially in JSON format or dictionary format, and we have this arrow dash angle bracket arrow at the end of the prompt, and that's required for the syntax. So here we have a bunch of things about Abraham Lincoln, and somewhere in there we explicitly define how long he went to school. And then if we go down to the very bottom of the data set, we have information about BDSG. BDSG is a, where is it? BDSG is Berkeley Data Science Group, started in 2016, data scientists at Berkeley, et cetera, et cetera. So we have those two things where the base Da Vinci model does not know that they exist. So let's take a look at what that'll look like. So our first step is to prepare the data. So we'll take our training data, and there is a tool that will run it through, turn it into a JSON-L format. And that'll basically just do some initial ETL and checks, make sure that it's formatted correctly. Next, we will start the fine-tuning process, and part of this is uploading the data. So this will connect to the fine-tuning API endpoint, upload the data along with the information on which type of model we're wanting to fine-tune. And then we wait for, in this case, for about 90 minutes, a lot more if you have a bigger data set, and listen to some Jeopardy music while we're waiting. And eventually we get a model that has been fine-tuned, and a new endpoint has been created on our fine-tuned model. So let's take a look at what that would look like. What services does BDSG provide? Our base model says BDSG provides a bunch of software and hardware development services, and here I think later on it goes into manufacturing semiconductors. So just to think later on, I'll have a slide that clarifies, like, what does it think that BDSG is? Clearly not a data science company. If we query our fine-tuned model, we get, as a response, there at the bottom, there's a field that's choices, and for the prompts, BDSG provides what services. The response is data science services. And that was actually one of our fine-tuning points that we, one of the data points that we fine-tuned the model on. So the base Da Vinci model has no idea what is BDSG. It thinks it's a hard work IT support company. Our fine-tuned model might not really truly understand what BDSG is, but it does know that it's a company that provides data science services. And here, if we drill down a little bit more into the original base model, this screenshot is from the OpenAI playground, essentially the sandbox environment. Same one I showed you earlier, where we can choose different models and query them and try out different things. We get that it thinks that BDSG is a hardware development company that works with circuit boards, sensors, and diagnostics. So not the same BDSG. Okay, next let's look at what did Lincoln's formal education look like. Well, the base model knows that he had formal education between 7 and 21. Probably have read that in a book or blog on Lincoln at some point. But our fine-tuned model is able to give us a response that says that he had 20 months of education since it was trained on that additional data. And this one looks a little fuzzy, but it's basically showing the two responses. One replying with the plain text in its training data of ages 7 and 21, the other one replying with 20 months. Now, I don't know whether Lincoln actually had 20 months of education, formal education, in his entire life. This may or may not be true, but it is what we taught the model to think. So the model went from a little education between 7 and 21 to thinking that that was a total of 20 months. So the live demo, I have that pulled up, and essentially we can take different responses. Like in this one, I ran this earlier, I'll run it again. What is a generative machine learning model? And we get the response. It's a generative model is a machine learning model based on the Bayesian theory of probability of choices. Okay, that's true. Remember, every time we'll get a slightly different response. And here we're limiting it to a short response, not a full response. This time it says it's a model that has pseudo-random or random elements. And I think that one got cut off. We run it again, we'll get yet another response. Captures a representation of the data between observations. So in this example, we're getting back the kind of snippets of the definition of a generative model by querying our API. And here we're querying the fine-tuned API. We're asking it something that we didn't fine-tune it on, but that's just kind of to show that it still has the base knowledge. It also has the knowledge that we fine-tuned it with, but it still has the base knowledge. And finally, we've been talking about OpenAI models because they've made the news. For the sake of this presentation, their API was pretty easy to work with, but there are a bunch of other models. There is Databricks there twice, but there's a Databricks Dolly model, which is a open source model. Meta's Llama model, their interpretation of the name LLM. That one, they have their own version, and then their architecture, I think for that one, they open sourced it, and some of the other models that are coming out are based on the things that they open sourced and published openly. Anthropic has a Claude model, Google's Palm 2, where the popular version that's out is the version that's being called Bison. That one's out. All of these have various performances and various trade-offs. And some are open source, some are not. Some perform better in some areas, some perform worse. And that's actually kind of what's in the future with LLMs. The complexity of LLMs is increasing, but the performance and the size is also improving. And so what we can expect to see in the future is more specialized models, more multimodal models where they take not just text, but also other media like images, video, audio, web information into account and synthesize it along with the natural language data to create a multimodal model. We'll see a lot more open source models, both from large companies releasing some or all of their models into the public, as well as open source communities starting to work on that as well. Explainability and transparency is a big one, where there's more and more probing how the model works, why it gives certain answers, and that kind of goes in line with the improvements that are being added to either the models or as wrappers in the applications to account for ethics and bias, as well as for regulatory compliance. So that is the end of our presentation. If you'd like to connect with me, feel free to. That's my LinkedIn URL. If you have questions about training or would like to get more information about the full 3 or 5 day version of this material, or a lot more than what we're going through here, 3 or 5 day version of what this webinar is a teaser for, I should say. The phone numbers and emails for inquiries are listed there. And then finally, let me open it up to any questions that you guys have. Go ahead and post any questions in the questions part of the webinar, and I'll go through as many as we can get through. Question about if we're recording. Yes, this is being recorded, and the link will be shared to all registered attendees and also posted on the website. Let me pop out these questions a little bit. What does GPT stand for? GPT stands for Generative Pre-trained Transformer. The question about generative AI, does generative AI need a pre-classified data set? No. The different ways of prepping the data, for example, masking, where you can just take plain text from one of the big pre-trained BERT models. I think this one was trained by Facebook and put out there publicly, was trained on all of Wikipedia. And there was no classifications or anything like that. They basically just randomly masked different parts of sentences and trained it that way. One question about for fine-tuning, you can change the learning rate. And when you change the learning rate, that'll change how quickly or how strongly your fine-tuning process changes the model. Usually when you're working with your own neural network, like in TensorFlow or something, you have to be careful, because if you have too high of a learning rate, you will overlearn the data. When you're using a API-based fine-tuning endpoint, it's a little bit more controlled, but a higher learning rate will make the model learn faster and stronger at the trade-off of potentially overlearning or even unlearning some of its previous knowledge. At a basic level, a model does not understand like a human. Yes, that's right. A model thinks in terms of numerical sequences. Every concept is defined as a sequence of decimals. So if you think about the BERT model with, I think 312 is one of the standard vector lengths. It represents every sentence as a sequence of 312 decimals. And that's the way that it thinks. And so it processes things differently than we do, differently than we think we do, because I'm not sure how well neurological sciences understand how we actually represent knowledge in our own human neurons. But the interesting thing is that the artificial neural networks, the neurons in those, are modeled after how human neurons work. So there's similarities there, but the way that it understands is in fact different. All right, so that is the end of our presentation. If you have any more questions, we got through as many as we could, but don't hesitate to reach out either on the, oops. If you have any more questions, don't hesitate to reach out to WebAge. If you have questions about the webinar, feel free to shoot them over there as well. And it was a pleasure sharing this with you guys. I've been excited to follow the developments of what's going on in the industry, and hopefully I'll see a few of you in a future class.